In this video, we are going to study a few more examples of vector space and few properties of vector space. In my last video, I have taken a set of two tuples, order two tuples, they form a vector space that we have proved. Similarly, you can prove the set of all ordered triplets over the field of real numbers. They also form a vector space with respect to addition and scalar multiplication as defined in the first example. You can even say that set of all ordered n tuples, they also form a vector space. I'll take up one more example. See, remember one thing, when I have to show that in a vector, I have to show that it's a set forms a vector space, then I have to check for the abelian group condition with respect to addition, and then I have to prove for any vectors if I have say any scalars from the field F, alpha belongs to F and vectors belongs to vector set V, then I have to check whether this is true. I have to check alpha, suppose alpha and beta are there in my set, then alpha plus beta into V1 is alpha V1 plus beta V1. If I have alpha into beta V1, then this, and at the end I have to check for this, for all V belongs to V. Okay, I have to check these conditions. If this satisfies for the vectors from the set and scalars from the field, then I can say that this set forms a vector space. Remember one thing, if I have say alpha beta belongs to the field F and say vectors V1 and V2 they belongs to V, and if V is a vector space, then always remember that alpha minus beta into V1 is same as alpha V1 minus beta V1, and alpha into V1 minus V2 if I take, then this is same as alpha V1 minus alpha V2. This is true for any alpha beta belongs to field F and V1 V2 belongs to vector space V. If V is a vector space, then these two are also true. Okay, you can. So let us go for the problems, that is proving some set as a vector space. Okay, the set will be given to you and there will be a defined operation, and based on that I have to check whether it is a whether this forms a vector space or not. Okay, the first problem I'm taking is this: let V be the abelian group of positive real numbers for the multiplication. Okay, this forms a group, abelian group with respect to the binary operation multiplication. How the scalar multiplication is defined? It is defined like this. Okay, usually what we take is, we take a set which is to prove that it is a vector space. For that I go for abelian group under addition, I check for that. But in this case they have already mentioned this forms a abelian group under the multiplication, and the scalar multiplication is defined like this. They have mentioned that it forms a abelian group, so no need to check for the abelian group. I just have to show that V forms a vector space over the set of real numbers, for which the scalar multiplication is defined like this. Okay, so checking for the abelian group is not necessary, it is already mentioned. Okay, so I just have to check other four properties. They are like this. Abelian group I have already checked. Okay, and I have to check for these three properties in fact. Okay, so let us check. First, they have mentioned for any A belongs to R and X vector X belongs to V, AX is X power A. Okay. Let me take, I'll take scalars from the field A comma B belongs to, here the field is set of real numbers R, and I'll take a vector say X comma Y, they belongs to the set V. I have to prove that this forms a vector space. No need to prove for the abelian group because they have already mentioned it is an abelian group. So for any A comma B belongs to the field R and X comma Y belongs to V, let me check with the first property, that is A plus B. You can even take alpha also, but since they have mentioned AB, I'll take that only. This is by definition X power A plus B, which will be equal to X power A into X power B. In fact, what is this? X power A is nothing but AX into X power B is BX. So this is true, no problem. When I take the second property, it is scalar into product of the vectors, because it is mentioned it's a abelian group under multiplication. So I'll take XY. By definition, this will be XY power A, which will be equal to X power A into Y power A, which is nothing but AX into AY. So this is also well defined, no problem. And the 1 into the vector, which gives me X power 1, which is nothing but X only. So 1 into V is V, no problem. And the fourth one, that is alpha beta into V, which is AB into X, which is X power AB, which will be equal to, same as writing X power B into A. That gives me A X power B, which will be equal to ABX. If you want, you can put it like this. So all the properties are correct. Therefore, I can say that this V forms a vector space over a field R. By looking at this example, you may get the doubt, like, if I have any abelian group, can it be made into a vector space by some scalar, by defining some scalar multiplications, like say here I have taken this scalar multiplication. If I take some scalar multiplication, say A into vector V is equal to 0 for any scalar belongs to the field F and V belongs to vector space V. If I have a group, okay, which is a abelian group, and can I make it into a vector space by defining the scalar multiplication like this? But in fact, it is not true, because when I define it like this, all the axioms will be satisfied. Only the thing is, with this it is not defined, because when I take one scalar as 1 into vector V, then this will be V. Okay, it has to be V to say that it forms a vector space. But by the scalar definition, which is defined like this, I'm going to get 1 into V is equal to 0. So remember one thing, it's not so easy to make a abelian group into a vector space by defining some scalar multiplications like this. Okay, all the axioms will holds good, only the thing is with this multiplication. Okay, yeah. Now let us look at the properties of vectors. first property, let V be a vector space over the field F, and V belongs to V and a scalar A belongs to the field F, then these are true. Okay, let us prove these things. Okay, first one, prove the first one. Say I have to prove A into 0 vector is 0. Okay, for any A, scalar A belongs to the field F and 0 vector belongs to V. Let me take this is not 0. Okay, let us assume that A into 0 is, say, some vector W. Then I can rewrite this as, say, W equal to A into 0. This can be written like this also, which is same as writing A into 0 can be written as sum of 0 vectors, 0 plus 0, which will be equal to A into 0 plus A into 0. Okay, which will be equal to W plus W. I can use the cancellation law for the addition. So if I cancel this with this, then I am going to get W equal to 0. If I cancel this with this, so I am going to get W equal to 0, which is nothing but A into 0 is 0. So hence the first property. Next, the second one. I have to prove 0 into V is equal to 0. Okay, so let me take 0 into V is not 0. Let me take it as, say, some W dash, since I have taken W in the previous case. So I can write the same way, I'll do it. W dash is 0 into V, which can be written as 0 plus 0 into V, which is nothing but 0V plus 0V. Since I have taken 0 into V is W dash, write it as W dash plus W dash. Same cancellation property, I am using cancellation for addition. If you want, I'll write by cancellation law for addition. For addition, I can write, if I cancel this with this, I'm going to get W dash equal to 0. Hence the second one. The third one, I have to prove that minus A into V is A into minus V, which is nothing but minus of AV. For that, see, I'll use the second property. I'll use second property which says 0 into V is 0. Okay, so same as writing 0 into V, which I'll write 0 can be written as A plus minus of A into V. Okay, A plus, because by addition the A minus A is the inverse of A. So this is same as writing A into V plus minus A into V. Now by the uniqueness of the inverse, I can write minus of A into V is equal to minus of AV. By the uniqueness of, if you want, I'll write by the uniqueness of the inverse, I can say minus A of V is minus of AV. Similarly, I can even prove that, I'm not going to prove, I'll just write similarly, I can even prove A into minus V is nothing but minus of AV. Okay, and the fourth property, I have to prove AV equal to 0 implies either A equal to 0 or V equal to 0. So let me take AV equal to 0 and I'll take let A is not equal to 0. Then I have to end up with V equal to 0. Okay, since I know that F is a field, there exists, I'll write, since F is a field, there exists some element for A such a way that A into that element gives me the identity. Say there exists an element, say A dash in F, such that A into A dash is same as A dash into A, which gives me the identity. Since I know for the field F there exists, for every element there exists another element in such a way that this is true. Okay, now I'll take vector V, okay, which is same as writing 1 into vector V. This 1 can be written as A dash into A into vector V, which will be same as writing A into A dash or the other way. So A dash into A into V. V is equal to, A into V is given 0, therefore this is same as writing A dash into 0, which will be equal to 0. Hence what we have got, V equal to 0. So if AV is equal to 0, if I take A is not equal to 0, then V is 0. If A equal to 0, then V will not be equal to 0. So that's the thing I can write. Hence AV equal to 0 implies either A equal to 0 or V equal to 0. If A is not equal to 0, then V equal to 0, or else I'll get A equal to 0. In fact, I'm going to use these properties only to prove the thing which I have mentioned earlier, that is this, to prove this. Okay, let us prove this. Into vector V1, this is same as writing alpha V1 plus minus alpha into V1, which is nothing but 0 into vector V, which is equal to 0. And I can even say this minus alpha V1, no, minus alpha of V1, which is equal to minus of alpha V1. And by distributive law, I can even say alpha minus beta into V1 is equal to alpha V1 plus minus beta V1, okay, which is nothing but alpha V1 minus beta V1. Now alpha into V1 plus minus V1, if I consider, which is equal to alpha V1 plus alpha into minus V1, okay, which will be equal to alpha into 0, which is equal to 0. Therefore, I can say alpha into minus V1 is equal to minus alpha V1, and by distributive law I can even prove alpha into V1 minus V2 is equal to alpha V1 plus alpha into minus V2, which will be equal to alpha V1 minus alpha V2. So if V is a vector space, and alpha beta are the vectors and V1 V2 belongs to the vector space, then these two conditions are true. Okay.